Welcome back, everybody, and welcome to the second week of Physics 4480 and 9480. And today we will try to wrap up some of the calculations which we did last week. And one of the motivations for that is to show you how cumbersome it becomes when we have many particles, the kind of formalism. So in a way, everything we're going to do today serves both as a way to see how you can calculate things, but also it's going to motivate the introduction of a more compact formalism. And that more compact formalism is that of second quantization. So that gives you a feeling that there are many different ways of quantizing things, but it's actually just a name which has stuck with this approach, which is in principle just a transformation to another space. And what you do then is that you take away, you transform away the spatial degrees of freedom. And the only thing you're looking at is the number of particles which can be in a given quantum mechanical state. And that gives a more compact formalism. And it means also that when you're dealing with the standard way of calculating quantum mechanical observables, the way you're thinking of it is in terms of particles interacting with themselves an infinity of times, and then leading to a final expectation value or finite observable. Here, we're going to replace that way of interpreting a physical system with the number of excitations. So it introduces another type of language, which is very much used in fields like condensed matter physics, in theoretical physics in general, in nuclear physics, and in quantum chemistry, atomic and molecular physics. So these are many of these fields where you deal with either low energetical systems, or even if you go to quantum field theory and particle physics, you will recognize much of the same way of thinking. Okay, so we are going to mainly look at fermions, but then I will later also say something about bosons. So the main focus here is going to be on fermionic systems. So that means systems with half spin for the different particles. It can be spin a half, spin three halves, etc. And in general, when you do condensed matter physics, it's normally spin half particles. But if you introduce particle physics or move to nuclear physics, you can have particles with spin free half. Okay, let's now take a look at where we ended last week and run through some perhaps not too exciting calculations, and then also introduce some notation which we are going to use throughout the semester. So when you calculate many body observables and expectation values, you're often looking after a way to compactify the formalism. So I'm going to switch now to the whiteboard here. So let's do that. And let me first give you a very short reminder of what we did last week. So we ended roughly with a discussion of the quantum mechanical operators. And if we look at the energy, it's pretty common to define a Hamiltonian operator. Let me just take that one away. And what I'm going to do now is to try to be consistent and put hats on operators. So I'm going to have put an H to indicate that this is an operator. And you know, if you have kinetic energy, you have a differential operator. There's a second derivative. So this is normally written out in a term H0 plus some term Hi, and often the I stands for interaction between particles. And H0 is normally a part of the Hamiltonian, which we can solve analytically given a basis as an ansatz. So this H0, which we defined last week, is a sum of single particle operators, or what we call normally one body operators. And now we are looking at an energy operator. So this is a quantity which we're going to use to calculate the expectation value of the energy. So this is typically given by a sum over all the particles which we have available. And there is a one-body operator of x of I here. Now, this x of I, just to remind you quickly, x of I is now going to be a shorthand for the spatial degrees of freedom and eventual spin degrees of freedom. So that is another space which then couples with the spatial degrees of freedom. So that means that there are some spin quantum numbers, sigma of I, which we just leave undefined here. So x is then a common denominator. So sometimes I will use x for a one-dimensional variable. So hopefully you will be able to see from the notation whether this is the general variable or whether it's a specific one-dimensional degree of freedom, spatial degree of freedom. So I will try to make these distinctions, and I will not put a vector sign on that one. And then the sigma of I is normally a discrete variable because the particles can have spin 1/2, spin 3/2, or spin 1, 0 integer values. So R is a continuous variable, whereas X is a discrete variable. And what we had then is a Hamiltonian, which then acts on a given state. So we're going to look at a state here, so phi of alpha, and this is a function of x of I, and this is given by some eigenvalue of phi of alpha x of I. So phi of alpha is an eigenstate of this system. Just to give you an example in one dimension, and this is the case we looked at last time, and we can look at the harmonic oscillator, and we use this acronym HO for the harmonic oscillator. Then this operator H0 of x of I, this is now given by minus h squared of 2m. And now I hope you can forgive me if I use x here, because this is now the spatial degree of freedom. This Hamiltonian doesn't have a spin dependence, but just keep that in mind. Plus a constant 1k, which we leave undefined, but which is proportional to the frequency of the oscillator trap and multiply with the mass of the particle. But we just leave this k just as a common denominator for these variables. Now, so forgive me a little bit now, because x now is just the spatial degree of freedom. So in this case, we have no spin dependence. Now this state, phi of alpha x of I, is actually a state which is a tensor product of the spatial degrees of freedom. So this phi, which you see here, of alpha, we're given quantum number alpha, is now something which depends only on the spatial degree of freedom in one dimension. And this is a tensor product with the spin degrees of freedom. So we are just going to write this as a sigma of alpha here, or just a sigma. So this spin function is something which is going to leave undefined, and we are coming back to that one. So phi of alpha is actually, this phi of alpha which you see here is the eigensolution of this problem here. And now, since I'm just in one dimension, x here refers only to the spatial degree of freedom. So if you want to write this in terms of a specific system with a given number of particles, so this is a solution to a one particle problem. But now you could think of, if we now make a table or a list of these states, you could now think of making a figure here where you have alpha equal to 0. And I'm going back to the energies here. And then you could have, suppose, 4 states. And this defines the Fermi level. And we are making an ansatz for the ground state of the system. And in this case, we can look at a system with 8 particles. And since this is a one-dimensional problem, what we could have now is a one with a spin up So the arrows indicate spin up or spin down. And then we have a new particle here, a new one here, new one here, a new one here. So this mimics a little bit the exercise which you have this week. So this will be alpha equal to 1, alpha equal to 2, alpha equal to 3. And then you have an infinity of states for the harmonic oscillator. So this goes up to infinity here. So alpha equal to 4. So you would then make an ansatz where this could now be the ground state, this phi 0, which we discussed last week. This phi 0, as we will see pretty soon, it is actually an eigenstate of H0. So the ansatz which we are going to make is going to give us something which can be used as a basis for making an expansion of the exact solution in terms of a basis which is orthogonal, because we could now think of promoting one of these particles up to another state. That would be another many-body state. So this is just one configuration, and the energies which we have, these epsilon alphas for the different states, since this is a harmonic oscillator in one dimension, this contains just one quantum number plus the 1/2. So this n alpha is actually equal to that number alpha which we put down here. And that goes from 0, 1, 2, and in principle up to infinity. So the harmonic oscillator is a system where we have an infinite number of single particle states. And they are all bound in a harmonic oscillator potential. That means they cannot escape, unless by quantum mechanical tunneling. But we say that all these states are bound because these states are states which are defined within this potential web. In real life, we can have potentials which look like a harmonic oscillator, but they will only have a finite number of states, which are so-called bound states. So that means that these are states which are defined by discrete eigenstates of the system. States which are not bound are typically defined by a continuum of solutions. So a bound state translates into what you might call a differential equation with boundary conditions, which put a constraint. So you could also say, if you don't want to talk about the quantum mechanical discretization as an ansatz about systems, you can just think of a differential equation with boundary conditions. Actually, if you have a spring or a beam which is fastened in both ends, and you solve that differential equation, the wave equation, mathematically, you will actually get discrete energies. However, these discrete energies have such a tiny difference that you cannot measure them. So the experimental resolution is not good enough for you to see these differences. So if you put a spring into oscillations, that will have a discrete set of eigenstates, but you cannot measure the difference between them. If you put in a normal length for the spring and a normal weight, which could be something like 10 centimeter. So the microsystems which you meet quantum mechanically, you can actually experimentally observe these differences between states. Okay, so that's just another way of thinking of the quantum mechanical quantization, which in a sense is just you having discrete states for what we call bound states. And then you can kick particles out of a potential well, and then there will be an infinity of states which the particles can have. And that's simply because you don't have any boundary conditions anymore. Okay, that's just another way of looking at things. I guess you guys are used to two-point boundary value problems. So you may have seen that in the literature or in different courses. A spring which is fastened in both ends, or just a beam which you can just put into oscillations. Okay, so with that kind of system, what we did last week was to set up what we call the lowest lying state and the ansatz of that for a many-body system for n particles. And these are fermions. So that means that we need to bake in this anti-symmetry, which was postulated by Pauli, and which leads to, for a single particle picture, that you cannot have more than one particle which is in a single particle state. This is a consequence of the Pauli principle. That is not the Pauli principle. It's a consequence if you adopt a single particle picture. So what we did then was to make this ansatz, this phi 0, and then we had an x1, x2, up to some xn, and then we have some additional quantum numbers, which are these slots, which we discussed, up to some alpha of n minus 1. And if you go back to the picture which we made here, this would be a typical example of the different alphas. And then you can also add spin, because now we are going back to the x's as a generic variable for the different particles, and which includes both the spatial degrees of freedom and eventual spin degrees of freedom. And what we saw then is that you can make an ansatz where you would write this in terms of n factorial, the number of permutations you can make. And then we have a determinant here of phi alpha 0, x1. And then we use the rows to indicate these specific quantum numbers up to phi alpha 0, xn. And then we have phi alpha 1, x1. And this is phi alpha n minus 1 of x1. And this goes all the way up to phi alpha n minus 1 of xn. So this is an n times n determinant. And what we did last week was that we could rewrite this in terms of a more compact notation, which is going to be pretty handy for us. And we can write it out in terms of the number of permutations. So let me quickly remind you of that. P factorial. So this is the number of permutations we can make when we have a given number of particles. And there is a factor P, and there is a permutation operator. So that permutes rows and columns in the determinant. And then this was multiplied by this quantity, which we call the Hartree wave function. And this depends on alpha 0, and I just put dots here. So this state is just a product state of the single particle wave functions. And what we did was to make an ordering of that in terms of the diagonal matrix elements of the determinant. So that means that what we had is a phi h. This is normally called a Hartree state or Hartree function. And that is just given by the product of the diagonal elements, x1, phi alpha 1, x2, and all the way up to the last state of xn. Now, what we could do now is to rewrite this state in an even more compact way. But I wanted also to remind you of the fact that the Hamiltonian commutes with this operator. So we're assuming that we have a symmetry under the permutations of two particles, which is preserved. So that's an important aspect. Now, we could actually introduce an operator, which is called the anti-symmetrization operator, and I will say why I have this now. You will see that from the calculations here, anti-sym operator. And we define that as simply 1 over n factorial, and this is the sum over all the possible permutations of P, and then like that. So just to give you an example, if I take n equal to 2 here, or a 2 by 2 determinant, so then this operator is just going to be equal to 1/2. I have two particles. And then I would have P12, which just leaves everything unchanged. So I'm just going to write that as 1. And then it has a minus because I'm doing one permutation. So this is little p equals 0. And this is P to 1. So if you think of a 2x2 determinant, just let me quickly remind you of that. So if we do that, we have an A11, A12, A21, A22. So then you have A11, A22, minus A12, and A21. So for this case, what you have done is an interchange between 2 and 1. Whereas in the first case, you just leave it in terms of the diagonal elements. And this is the kind of ordering we are going to keep. So that means that what you have then, if you go back to the way we have organized the Slater determinant, we have defined this function here, which is not antisymmetric, and that will give us wrong expectation values for fermionic systems. But we can use that as a product of the diagonal elements. You can see this again if you do a 3x3 determinant, just to get some feeling with what you might get. So if you do a 3x3 determinant, so we have A11, A12, A13, and then A21, A22, A23. So when I say all permutations, it's not only you permuting two particles, but it's all possible ways you can permute the 3 columns and the 3 rows. So if you look at that one, this is simply given if we choose the upper row as a starting point here, we will then have A22, A23, A32, A33, and then it's minus A12, and then it's an A21, an A23, and then an A31, and then an A33. And then we have plus an A13 multiplied with A21, A22, A31, and A32. Now, if you, for instance, look at the first term you get, you would get, if you take this one, A11, you have multiplied with A22 and A33, nothing happens. In the next case, 1, 1 is staying there, but you're interchanging 3 and 2. So if you then look at all these expressions and you write them out, you could write this in terms of the following. So if you use this notation, P1, 2, 3, it means nothing happens. And this is what we call, so we have 0 permutations, which then corresponds to this one, multiplied with that and that. Then we have the next one, which then gives us minus, and then I have P, 1 stays in the same place, but I interchange 3 and 2. And then you see that you have, when you multiply out here, you have 6 possibilities. So that is the number of permutations you can make, which is the number of particles and the factorial of the number of particles. So that when you then spell everything out, you will get permutations like this one, P312 minus P213 plus P231 minus P321. And this goes back to all the terms you get when you multiply out the different cofactors of the determinant. So this would be the 3x3 case, and then you can continue like that, which is not so exciting, but you see what we actually mean by permutations, okay? So this kind of notation which you have here, the one we brought in here, is a more compact way of writing out a determinant. And this operator is also an operator which is interesting because it has a property. If you now look at this operator, since it just contains P, it commutes with the Hamiltonian. And it's easy to see, and you can test that for the n equal 2 case, that if you take A squared, so this is another property, is equal to A. So if you're a little bit in doubt, just take this operator here, and you will see that immediately. If you take A squared for 2 particles, so 2 here, n The subscript is for two particles. That is 1 divided by 4. And then I have 1 minus 2 times P21. And then I have plus P21 squared. But P21 squared is equal to 1 because I interchange 1 and 2, and then I interchange 1 and 2, and then I'm back to where I were. So, and then you see that we get 2. So this is simply 1/2 of 1 minus P21. And I'm going to try to be consistent and keep halves on here. Okay. So this is just to give you a kind of feeling on how we can massage these equations. And the thing is now with this operator A, we can rewrite this phi 0, this ansatz. And now, just for simplicity, I'm going to skip all the x's and the additional quantum numbers because it's pretty boring to write down all these numbers. So it's understood now that we specify all the quantum numbers. And we can rewrite that in terms of this operator as this A acting on this state, which is just a product state, which now is just the diagonal elements in a Slater determinant, the product of the diagonal ones. Now, if you then go back to the system here, you will see that if we now take the diagonal elements like this as our basic ordering, this is something which goes back to the physical model. Because now you could think of you having specific slots. So this will be slot 1, 2. Let me just write this in red. 1, 2. We have 3, 4, 5, 6, 7, 8. So you have 8 slots where you have placed a particle. This means that you can use this as your ordering. So every slot now represents one of these single particle wave functions or these single particle states. So that means that when you go back to this definition, then these slots are ordered in a specific way. And this is a way which follows your physics intuition about the system, because you're going to assume that this makes sense as a physical approximation to the ground state of the system. So if you go back to a case which is perhaps common to many of you who have studied physics, you can think of atomic atomic helium. If you think of atomic helium, so let's just look at that one. This is the simplest two-particle case which we have. And there we have an approximation where we now could think of the atomic state, according to Niels Bohr, where we have 2 electrons here, one will spin up and one will spin down. This is a 1s state, which has quantum numbers n equals 0, number of nodes, the angular momentum, orbital momentum 0, and the projection of the orbital momentum equal to 0. And then you could think of you having the Fermi level here. And then you have new states, 2s. And if you keep the degeneracy, which you have in the hydrogen-like problem, then you have actually 8 states with the same single particle energies. So that means that you have 8 slots here, which define different single particle states. Then you have the next shell, which is 3s, 3p, and 3d. So these are quantum numbers, and this just goes on to infinity. The hydrogen-like basis in atomic physics is not a convenient basis. Well, it is in a certain sense, but it doesn't have the right physical properties. Could you think of why? So it's a computational basis, like we defined last week. It has an orthogonal set of single particle states. So you could just think of using hydrogen-like solutions. But it's not a good enough physical basis. Could you think of why? So this is a question to the physicists here. So I'm going to give you a hint. So if you look at particles trapped in a well, so this is schematic. This could be a harmonic oscillator well. So you have a certain number of finite discrete states which are bound. And then after that, there is a gap, and then there's a continuum of states here. So if you think back to the hydrogen problem, what kind of solution do you get? Do you get bound states and continuum states, or do you only get bound states? If you think back to the energy, this is you looping back to Physics 2-140, for those of you who went here, or the basic quantum physics course. I just want to give you an answer here. So if you put the level here of zero energy, so the energy for this kind of problem is given by a constant minus E0 divided by, I think it's n squared, where n are these quantum numbers, n equal 2, etc. So what kind of states does the hydrogen type of problem represent? Any idea? If the energy is negative, if you put E equals 0 here, so it's only bound states. So if you wish to describe a system where a particle can leave out of the well, then this basis is not an optimal basis. It's still a computational basis of orthogonal states, but it's less relevant for cases when you want to study particles which escape. Actually, this is in quantum mechanical calculations and applications of the theory. It's actually a big problem. So how do we deal with states or particles which escape the system? Because that would lead to ionized helium. And one of the brute force approaches has been to actually set up a big box and simply say that if the particle is outside a certain radius, then we treat the particle as not being bound. And then we have ionized helium. That is not a good enough approach. So actually, this is a very big problem in research. And how do you actually define a system, whether it's ionized or not? So ionization means here that you kick out an electron, and then you're just left with a charged ion. And when do you define whether this electron, which is far away, together with a charged ion, is to be regarded as an ion by itself and an electron far away? So this just to give you some of the kind of things. When you do many-body physics, you have often a good orthogonal basis, but that orthogonal basis may not be the best one for specific types of calculations. So if you want to study ionization of atomic systems, then the hydrogen basis is not the best starting point, because it represents only bound states, but you have an infinity of the bound states. The harmonic oscillator is the same. It represents an infinity of bound states. So that's an idealization. So even if you can solve analytically the hydrogen-like problem, it's not a good solution for ionized hydrogen, where you kick out one electron. Okay, so what we are going to do now with these equations, we are now going to, look at a two-particle problem. So you could think of this as helium, or just a general two-particle problem. And what we want to do now is simply to calculate this expectation value, where we have an ansatz with a Slater determinant, plus these two operators. And now we're going to do this in an extremely brute force way. So we're simply going to write out all the terms so that you can see from that what you may expect when you have many particles. So that means that we are going now to have a phi 0, which is given by 1 over square root of 2. And we have a determinant, phi alpha 0, x1, phi alpha 1, x1, and then we have phi alpha 0, x2. And we are going to calculate that expectation value. That expectation value is quantum mechanically defined as an integral. So that means that if we now take the one-body operator, it's going to look like as follows. So we're going to have a sum from I equal 1 to 2. This is the operator, which acts on particle 1 and 2. And then we're going to have an integral, dx1, and then a new one, dx2 here. These are just dummy variables. And then I'm going to multiply the Brown-Niket side. So I'm going to have a factor of a half. I have a factor of 2 factorial. And then I'm getting the determinant for the left-hand side. So phi alpha 1 of x2 minus, and then I have phi alpha, no, not that one. This is continuing here, minus of phi alpha 0 of x2, complex conjugate, phi alpha 1 of x1. And now this is multiplied with the operator, h0 of xi. So we have a sum here over I. And then we multiply this again with the ket side. So we would have a phi alpha 0, x1 of x2 here, minus phi alpha 0, x2 times phi alpha 1, x1. So we are going to get 4 terms for each operator. So let's just write it down for the case where we have x1 here. So that acts on particle 1. So let's take a look at that term, because the one for particle 2 is going to look like the same. So let's now break it down. So this is actually, I'm going to do this in a brute force way, because it also allows me to introduce some shorthand notations. And then we are going to use the more general expression in terms of this anti-symmetrization operator, so that we can actually calculate this in an easier way. But everything we do now seems to be a little bit cumbersome, and it just cries for a more compact way of performing the calculations. And that's where second quantization comes in. So I'm going to let you go through this kind of mini torture now. And then when we introduce second quantization, we have a much more compact way of doing things. So let's just spell out term by term. So now we look at the case where we have h0 of x1. So if I look at these terms now, I'm going to have 4 integrals of dx2, and I'm just going to spell them out. So there will be one term, which is phi alpha 0 x1, and then I have h0 x1 acting on phi alpha 0 x1, like that. And this is multiplied with phi alpha 1 of x2 and phi alpha 1 of x2. So that's the first term. So I'm just picking the 2 first terms on the Brown-Niket side. Now we have assumed that this is an eigenbasis. This phi is an eigenbasis. So when this guy actually acts on that one, if we do that, so let's just frame that in here. If I look at this one, this gives me just a constant epsilon alpha 0 multiplied with phi alpha 0 x1. If these functions are not the eigenstates of this operator, then we have to evaluate the integral. And that is something which would lead to a more general expression. But when you look at these expressions here, we have assumed also that the basis is orthogonal and normalized. So if you look at the expression, the integral here, together with that one, what should that give us? Just 1. So that means that since the operator is now acting only on x1, then it means that this one just runs with that integral, and it gives 1, since we have an orthogonal basis. Now, this again is a constant, which means that I'm left with, again, just the norm times a constant. So the first term here gives us simply epsilon alpha 0. But this is multiplied, as we have here, with a factor of a half. Then, if I look at the next terms, I'm going to have a term here which contains phi alpha 0, but there's a minus sign, sorry. There's a minus sign here. And then we have x2 here. And then I have phi alpha 1 of x1. And this is multiplied with h0 of x1. And then I have phi alpha 0 of x1 and phi alpha 1 of x2. So in this case, the operator is again acting on this state here. So I'm getting again, so with these two here, that is going to give me an epsilon alpha 0 times phi alpha 0 of x1. But if I look at the rest now, what happens with the rest? What should we get from that? Since we have an orthogonal basis. Yeah. So this term is actually equal to 0. Then we are going to get a new term here, which is going to run like a plus. So let's write that one out. There's going to be a phi alpha 0, x2. This is a cross term. I have a phi alpha 1 of x1. And then I have an h0 of x1 acting on phi alpha 1. Oh, sorry, 0. But now this is x2 here. And then I have a phi alpha 1 of x1. So these two wave functions are just numbers, so I can always interchange them. So that means that now this is acting on this one. So that gives me an epsilon alpha 1 times phi alpha 1 of x1. And if I now look at the integrals, what should I get there? Would you agree that we get just epsilon alpha 1? Because now we have x1 here and x1 here. These are orthogonal states. We perform the integration. We have a constant times the norm. And then we have the norm of x2 as well. But now x2 is in the state alpha 0. So this also gives, but this gives us epsilon alpha 1. This term here gives us epsilon alpha 0. And then I have a final term, which has a minus, and that is given by phi alpha 0 of x1, the phi alpha 0, no, alpha 1 of x2, multiplied with h0 x1 and phi alpha, and now we have interchanged them. So we have an x2 here and phi alpha 1 of x1. So what should that give us? If you look at that one. Sorry. Yeah, this is also 0. Because I have the operator here acting on this state gives alpha 1, but then alpha 1 here, now x1 is in alpha 0. So it takes some time to see all these things. But if I collect everything here with this guy here, so for h0 x1, what I'm getting then is 1/2. And then I get epsilon alpha 0 plus epsilon alpha 1. Now, when you then take x2, it shouldn't come as a surprise that you get the same. Because these are dummy variables. So you could just interchange them, right? So that means that you get epsilon alpha 0 plus epsilon alpha 1. So what we have here now is that the expectation value of H0 on this phi 0 is given by this energy phi 0, where this epsilon 0 here, this should be an uppercase epsilon, is simply the sum over all the alpha i's which you have in the system. So this is a lowercase because it represents a single particle state, and the uppercase is now the energy of a many particle state. So that means that the basis we have chosen is an eigenbasis of H0 for 2 particles. And then we can show after the break, we're going to show that this is the same for many particles. So this becomes important for us because then we have a basis of these determinants, which we can use as an orthogonal basis and expand the exact solution in terms of a linear combination of Slater determinants, where the Slater determinants are built on an ansatz based on a single particle picture. So in these fields which I mentioned, like solid condensed matter physics, nuclear physics, atomic physics, molecular physics, this is a good approximation. However, there are cases in condensed matter physics where you have strongly interacting systems, and then this picture breaks down. And then you have to use other methods than those which we describe here. But if you're looking into semiconductors, many materials, this is actually a very viable starting point. So these are the kind of building blocks. You make an assumption about a physical system where you think that single particle degrees of freedom are relevant degrees of freedom. And this is much inspired by atomic physics and molecular physics, where the electromagnetic forces are the most important forces. We take a small break. I just went a little bit over time, so we start again at the 11:20, if that is okay. So what we have now is a calculation of the one-body operator for this two-particle system. Before we generalize, we can now set up the expectation value of the so-called two-body operator. And now we're going to make a specific choice, which is the kind of choice which will follow us for the rest of the semester, basically. So when we look at the next term, so this is the compact quantum mechanical way of writing this expectation value. We need to define h of I. So this operator is an operator which we will define as a sum of all the particles. And there are no self-interactions. That's important. And we are going to assume that this operator depends only on the spatial degrees of freedom, and where this Rij is the relative distance, the absolute value of the relative distance between two particles. So this is a fundamental type of approximation which is made for many physical systems. So if you think of the electromagnetic force between two particles, that is invariant under the interchange of two particles. And many forces in nature depend on the relative distance between particles. The gravitational force is an example of that. The electromagnetic force is an example of that. In nuclear physics, we have examples of forces which behave like that. And there are many, many approximations or even fundamental forces in science which actually obey this invariance under the interchange of two particles. And there have been many experimental attempts at finding the breach of this invariance. And still within experimental uncertainty, this invariance still remains. So the assumption we are going to make then is obviously, after we have defined this Rij, so if I write this quantity, this is an absolute value. So when you don't see vectors, signs, this is going, if we are in 3 dimensions, this will be xi minus xj squared plus yi. So this is for 3 dimensions. You would have the same in 2 and 1 dimension. And this is in a Cartesian basis. And this quantity here, as you can see now, means that Rij is actually equal to Rji. So this is one of the fundamental assumptions, and this is a feature which is observed in nature as well. So we can now calculate this expectation value, and let's do that. So when we now set up everything, what we will have is this factor of a half. And since we only have 2 particles in this specific case, I and j have to be equal 1 and 2. So in our case, if we go back to the expression here, we are only having 2 particles. So this is going to be v as a function of r1, 2. So we can just write this down, and then we look at the integrals dx1, dx2 here. And then we have, again, the same wave functions which we had before, the same Slater determinant, alpha 0, x1, phi alpha 1 of x2 minus phi alpha 0, and then we have interchanged, and phi alpha 1 of x1, complex conjugate, and this is multiplied with v of r12. So this funny letter is my attempt at writing r. And then we have a phi alpha 0, x1, phi alpha 1, x2 here, minus phi alpha 0, x2, and phi alpha 1, x1. Like that. And we are going to get, as you can see here, we are going to get 4 terms again, right? So if we just do the plain multiplications, you're going to get 4 terms, and let's just look at these 4 terms here, because some of them are going to be equal. So we have 2 terms on the bra side and 2 terms on the ket side, and when we multiply everything out, we are going to get 4 terms, but 2 of them are going to be the same. So let's just write this out. So we're going to get 1/2, and then we have the first integral dx1, dx2, and we have phi alpha 0 of x1, phi alpha 1 of x2, v of r12 multiply with phi alpha 0, x1, phi alpha 1 of x2. That's the first term. Then I'm going now to multiply this term here with that term. I'm going to take these 2, and if you look at that one, we're going to get a plus sign. So we get the plus 1/2, and again we have dx1, dx2, but now we have alpha 0, and we have x2, and phi alpha 1, x1, and then the same potential, and phi alpha 0 of x2, and phi alpha 1 of x1. Now, if you look at the last term, so x1 and x2 are just dummy variables. So you can call them whatever you want, or you can just interchange them. So we just change x1 with x2. And then you see that this term is the same as the previous one. So these are 2 equal terms. And the reason why we can do this has also to do with the fact that this one is invariant under the change of particles 1 and 2. From the definition, because the only dependence on position here on the relative distance, we call this the relative distance, is now given by something which is invariant under the change of 1 and 2. So that means that this term is equal to the previous one. And then we have 2 additional terms, which we will also see are the same. We give the same contribution. So the factor of a half disappears. So we have minus, and then we have a dx1, dx2 here. And then in this case, we have an alpha 0 of x1, sorry, x2 phi alpha 1 of x1. And then it's a v of r12 multiplied with a phi alpha 0 x1 and a phi alpha 1 of x2. And we have a corresponding term here, and I'm just going to put an equality sign here, but where we have phi alpha 0 of x1 times phi alpha 2 of x2, the potential, r12, and then I have a phi alpha 0, so there should be alpha 0 here, of x2, and phi alpha 1 of x1. So the last line, it should be, oh yeah, this is 1, sorry, thanks. You see, yeah, thanks. Thanks for that. And now you see that if we do the interchange of x1, x2 here, the second term is equal to the previous one. So when we collect everything, we get two integrals. And now it's time to introduce a shorthand here. Because if you look at all these integrals, you're going to go crazy if you have to write them down, okay? So we're going to introduce a shorthand. And that's important. And that's going to save us a lot of space and a lot of writing. So we are just going to write something like this, alpha 0, alpha 1 of v, alpha 0, alpha 1. This is an integral. And that integral is simply given by dx1, dx2 here. And then I have a phi alpha 0, x1, phi alpha 1 of x2. I have an interaction which is assumed to depend only on the relative distance, multiplied with phi alpha 0 of x1 of phi alpha 1 of x2. So this is a kind of shorthand which we will use again and again and again. And that clearly means that if you look at the other one, the other integral, so this alpha 0, alpha 1 of v, alpha 1, alpha 0, that means simply that we have interchanged these two guys here. So with that kind of shorthand notation. And if you go back then to what we had, you can now choose whether you do the flipping here or if you do the flipping here. So this is just a matter of choice, as long as you're consequent. So if I add these terms, what I get then at the end is that this expectation value of phi 0 of hi of phi 0 for two particles is given by these integrals alpha 0, alpha 1, v, alpha 0, alpha 1 minus, and then I have alpha 0, alpha 1, and v, alpha 1, alpha 0. So these are two integrals, and they have names. So in this case, we would typically call this for the direct term. And when we do Hartree-Fock theory, it's normally called the Hartree term. And this integral here is called the exchange term. And that follows from the Pauli principle. And if we do Hartree-Fock theory, which is a mean field theory, this is called the Fock term. So this is Fock with an O. Okay. And we call people who do Hartree-Fock theory for Hartree-Fockers. And these are mean field theories, and mean field theories are always mean. Sorry for that. This is that digression. So this is a direct term, and the exchange term is due to the Pauli principle. Now, what we end up doing is also to write this in a more compact way. We can bring the two together, and then we define that as an anti-symmetrized matrix element. So if you look at these matrix elements here, they have some symmetries. So when you look at these ones, they are invariant under the interchange of 1 and 2, or in this case, alpha 0 and alpha 1. You can define a more compact matrix element, which we are going to call the anti-symmetrized one. And now I'm going to just leave out alpha 0 and alpha 1, but I will just define the states as P and Q. So this can be some generic single particle states. So this is an integral. If we are in 3 dimensions, this is a sixth dimensional integral, because we have 6 degrees of freedom with 2 particles in 3 dimensions. So we would write it like this, and Rs, and we put often an anti-symmetrized, and this has the following definition. So we have the direct term minus the exchange term, PQ. You can interchange P and Q, or you interchange S and R. So this is just a matter of choice, which one you prefer. So we are often going to use that one because that compactifies the expressions we are going to deal with. And in many cases is also handy because it means that you can pre-calculate these 2 integrals and store them just as one number in a table. Now these integrals have a symmetry then, and you will see that the symmetry follows from the definitions which you have here, from that definition. So if you take this PQ V of RS, this is the same as QP of V of SR. So that's the change of 2 particles. And you see that immediately from the integrals we have defined. But then we have also that PQ of V RS has to be equal to minus QP of V RS. And this number is also equal to minus PQ of V of S of R. And now I'm going to put here an AS, anti-symmetrized. So this is going to be an anti-symmetrized matrix element. So that means that the compact expression for this system of 2 particles, the expectation value of the energy with this basis which we have chosen of H of phi 0 is now equal to this epsilon alpha 0 plus epsilon alpha 1. And that's the expectation value of the non-interacting piece. So often you can split out the interaction and you can define some mean field, plus this matrix element, which we simply write in terms of the anti-symmetrized matrix element. Anti-symmetrized. Yeah. 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 Oh, sorry. I forgot to put that one. Sorry. Thanks so much. Yeah, because else it wouldn't make sense. Thanks. Good. So what we're going to do next, so you see this is a more compact way of setting things up. What we're going to do next is to do this for many particles. But now we are going to, for many particles, we are going to go back a little bit, and we are going to use the definition of these operators, which we set up earlier. So we're going to write a function like this in terms of this product. So then we can see now what will happen if we now look at more particles. So let's just do that. So the 2 particle case is useful to do because it gives us a kind of feeling of what we can expect. But let's now take n particles. And then we repeat this exercise. So for this case, where we calculate the expectation value of the energy, what we have then is obviously first this term. And in that specific case, what we end up with is now a integral over dx1, dx2, up to dxn. Keep in mind that these integrals, which we have defined here, before we, let me just set them up here, and then we would have multiplied with a phi 0 complex conjugate, H0 acting on phi 0. Now, these integrals, if you look at one of them, of d of x, that is the same as a sum over the spin degrees of freedom and the spatial degrees of freedom. So the compact notation is something we have to be a little bit careful with. And you will often see in the literature, and this is going to be one source of errors for the first midterm, is actually that in many cases you will see it's straightforward. We leave out the spin degrees of freedom, but it's straightforward to bring them back. Now, to bring back the spin degrees of freedom means that one has to be a little bit careful when one calculates this matrix element here. And the reason for that, so let me just explain that. So this state could be a spin up, and this could be a spin down. This is a spin up, and this is a spin down. Now, this is particle 1, and this is particle 1. So when you look at the spin states, you would then have 1, 0 multiplied with 1, 0 for the first particle, this one. And the next one would have a state which you could typically write like 0, 1, multiplied with 0, 1. So that's pretty fine. So these are the discrete spin degrees of freedom. But then you have to be careful because the integral here for the second term does not need to be 0. However, when you look at the spins now, then you have interchanged them, right? So it's pretty common to give the integrals without the spins, and then you have to put in the spin values afterwards. And you see now that in this specific case, you're going to have, for this one and that one, you're going to have 1, 0 multiplied with 0, 1, which is 0. So when you see in textbooks like we omit the spin degrees of freedom because it's straightforward to bring them back again, you always have to rethink a little bit because the difficult quantity to calculate is normally the integral over the spatial degrees of freedom. Now, with a basis like the harmonic oscillator and something like a electromagnetic interaction, you have even analytical answers for these integrals. And this is also why some of these basis sets are so popular in the scientific literature, because you can calculate easily some of these integrals. Obviously, if this becomes complicated, like Jun here is doing nuclear physics, if you have a given set of single particle states, it can take 1 day or even more to calculate all the integrals. So this depends on from case to case. Yeah.
What does it mean that the spin part becomes 0 in the
It simply means that the exchange part doesn't contribute. So when you set up the matrix element like this, it means the only contribution comes from this one. So you can calculate an integral, and the integral here without spin can be non-zero. But when you add spin, one term can become 0. If these are all spins up, then it doesn't matter, because then you will get 1. Or spin down, but if you have a spin up and spin down, then one of the terms can become 0. So this becomes important, like in the first midterm, you're going to get a table of matrix elements, which you will use in a many-body theory. And then the table of integrals simply gives you the numbers without spin. And then you have to, because it becomes convenient to actually rephrase everything in terms of one matrix. And we call these matrix elements. The reason for that is that you store these as a matrix. That's the main reason why it's called a matrix. It's an integral. And it represents a transition from one state to another state. So in a certain sense, you can think of these as transition probabilities. But in a sloppy way, we end up calling them matrix elements because that's the way we would store them in the computer. So if I say matrix elements, this is just sloppy language, okay?
Matrix elements, that's because of the matrix representation.
Yes, exactly, exactly. So when you use a matrix representation, then it's common to use that as a jargon. Okay, so if we look at these integrals, what we're also going to do now is simply to say that this dx1, just as a shorthand, dx2 up to dxn, we just rewrite this as a d of tau, where tau is dx1, dx2, etc., etc. Okay? So what we end up with then is an integral which we have to evaluate. So if we look at this phi 0 of h0, when we now plug in this definition of that operator A, which we discussed before the break, then we have an integral of all the degrees of freedom for the single particle states. We have the Hartree product multiplied with this guy. We have h0 multiplied with A and multiplied with the Hartree product. So remember now that this phi of h is just a product of the diagonal matrix elements of the determinant, which are just the single particle states from 1 up to n. And this A was that operator which we call the anti-symmetrization operator. So let me just bring it back so that you have it. So we defined this operator here. And we have a property that is A squared is A, and it commutes with all parts of the Hamiltonian. Because we have assumed, so this is a permutation of, let's say, two particles, and we assume that the Hamiltonian is invariant under permutations of particles. Yeah?
Can you just explain that sum?
It's the sum over all the permutations you can make. So when you go back to what we said with this determinant here, you can make 6 permutations in total. And these are the permutations, the base permutation, then I permute 3 and 2, I do 3, 1, 2, 2, 1, 3, etc. When you have only 2, you if you look back at the determinant, here you keep the basic ordering, which will be your Hartree product. And then you interchange 2 columns here, 1 and 2. And that comes from this term times that term. So that operator, which you see here, is now performing this interchange between the columns. And yeah. Sorry, this should be P, the number of permutations you can make. Sorry. And this little p is just the sum from 0 to all the possibilities you can make. Sorry, this was missing. I think I put it correctly previously. Yeah, previously I had p factorial. Yeah, this is sometimes, yeah. Thanks. So if we now use the properties that for this specific integral, which we have here, if we now use the property 1, that A commutes with H0, and we use also the fact that A squared is equal to A, then we can rewrite this integral as n factorial, and then I have a d tau, and then I have this product. This is just a simple product of single particle wave functions, and this is multiplied with H0 acting on A of phi of H. So I use the property here, that one. So then I can rewrite this expression here. And then a squared is equal to a. And this is nothing if we now put in, so n disappears because I have an n in the definition of a. So I have simply an integral over d tau, and then this product, and then I have h0, and then I have the sum over all the permutations up to p factorial. And this has a minus p, and then the operator p acting on the state phi of h. Yeah, so that commutator is actually equal to 0. Yeah, they commute because we assume that this is a symmetry which pertains to both the Hamiltonian and this operator. So then we can then look at this one in terms of the number of permutations. And then we have to bring back the operator. So if we now look at the sum, yeah, go ahead. Yeah. No, so this is just a sum which runs over all the possible permutations. And then this one, when you have here you would have a list of, it's a little bit kind of not always the best notation, but this represents all the sets of way you can permute the columns in the determinant. So if you go back to this 3×3 determinant, it's if you're a little bit in doubt, you can actually look at that one. And if you take a 3×3 determinant, this is essentially the way you would write it out. So you can keep this notation, or you can write it out in terms of all these possible permutations here. Yeah. No. So this, yeah, exactly. So you have a list of all the possible permutations. So I'm leaving because it can sometimes be confusing because people think this is just permuting 2 and 2 particles, right? But actually you have to, when it says like this, it means all the way you can permute the columns here. So it's a way to rewrite the determinant. So when I'm saying all the possible ways is when you look at these products, you can actually rewrite them in terms of looking at this expression here can be useful to get some intuition of what they mean. So there's a list of all possibilities. And if you have 3 particles, you have 6 possibilities, so 3 factorial. And that's something you can actually just write down. If you have 2, you have only 2 possibilities. I hope that helps a little bit. So the notation here, I know the notation is a little bit compact, but I hope that the 3×3 determinant can aid in developing a kind of intuition about what we mean here when with this sum over P here. It's just a way to rewrite the determinant in a more compact way. So if you make 0 permutations, that's the case which we looked at previously. So if we take P equals 0, what we would get then is the following. So we have 0 cases now. We just have the partial products. So then we would get this integral, which we saw before. We have a sum over I equal 1, the operators, dx1, dx2, up to dxn. And then we have this phi alpha 0, x1, up to phi alpha n minus 1 of xn. And then this is multiplied with h0 of x of I. So this I goes back to what you have here, just the sum over these operators. And then we have a phi alpha 0, x1, phi alpha 1, x2, and all the way up to the last one, n minus 1 of xn. So now we are just looking at the base state, which is the Hartree state, which is just a product. And now we know that, as we saw from the two-particle case, that this xi is going to act on this one, it will act on this one, and finally on the last one. And it's pretty obvious that this should give us just a sum from alpha I equal alpha 0 up to alpha n minus 1 of epsilon alpha n minus, alpha, the sum of alpha I. So this is the no permutation. Now, if we do p equal to 1, just 1, what we could have then as a possibility, so this is the sum of all the cases where we just interchange just two particles, okay? And then we can interchange 3, 4, 5, etc. All the possible permutations. So if I do that, one case, one example, could now be a dx1, dx2 up to dxn. So this is left unchanged, alpha 0, x1 up to phi alpha n minus 1 of xn. But then I have multiplied with h0, xi. And now I interchange these two guys here. x2, phi alpha 1, x1, and the rest is the same. And before the break, we saw that this is equal to 0 due to the orthogonality, right? So on that specific. And then irrespective of which one we do, we are going to get zeros for all the remaining ones. And if we do more than these, we will always have states on the right-hand side, which will lead to a norm, which is 0. So for p equals 0, that's the only case which gives a non-zero contribution. So it's pretty straightforward to see that when you have more than p equals 0, you will just end up with 0. So that's the case with the unperturbed or the non-interacting case. And now we can do the same exercise for the interaction piece. So for the interacting piece, we will get the following expression, AOI of phi 0. Because keep in mind now that the left-hand side and the right-hand side, they are the same. So later you will get an exercise where we can change one single particle state on the left-hand side, two single particle states, or 3. And then you will get results which depend on the type of interaction which you have, whether it's a one-body, two-body, three-body, etc. And that leads to something which are called the Condon-Slater rules, which are extremely useful when you're setting up transition probabilities between different states. So like for Jon, who is setting up a full configuration interaction code, that is a rule which is extremely useful when you're setting up your Hamiltonian matrix. Because then if you have a two-body interaction and your brass side differs by more than two single particle states, that's automatically 0. And this is actually one of the exercises. But now, in the lectures, we are looking at cases where we go from the same state to the same state, which is an expectation value. Okay? You probably heard of the Condon-Slater rule, right? That's extremely useful when you're setting up your Hamiltonian matrix. Okay, so in this case, we end up with much the same as we had before. We have a d of tau, and then we have this Hartree product, and then we have A. So this operator is actually, its Hermitian conjugate is equal to itself. And then we have H of I, and then phi of H. And if we do the same thing as we had before, we have made the assumption that these guys commute. You can actually prove that if you assume that symmetry, which we said. And then we're also assuming that this guy A squared is equal to A. And then we end up with a D of tau, the Hartree product, multiplied with H of I. And then we have the sum over all the possible permutations. And then we have the operator P. And this is acting on the state here, phi H. So I'm just going to give you the final result, and we pick up from this tomorrow. But what you will get then is that this is going to be given by the sum over all the states, alpha 0, and or alpha I and alpha j, which are included. We can write it like a half. We are summing freely, because if we then have a diagonal element, that is automatically 0 due to the anti-symmetrized matrix elements. So this is where we will start tomorrow, just to show the step from here to here. Now what you see, and this is my kind of motivation for, one of the motivations for second quantization, is that if you look at all this formalism here, it is okay, but it gets pretty unwieldy when you have to deal with all the integrals. So if we can compactify it and assume that some degrees of freedom have been taken care of, so the spatial degrees of freedom and the spin degrees of freedom, for instance, they will be taken care of by you tabulating these elements, these integrals. And then we can develop rules so that we can actually perform calculations, assuming that we can just look up in a table or some computer program where we can calculate these integrals efficiently. A pretty common way, which is done in many fields, is actually to tabulate, to pre-calculate these integrals and simply look them up. Alternatively, if you're dealing with electromagnetic forces, you can, with a given basis, which is very popular in quantum chemistry, which is called a Gaussian basis, which is often used to describe molecules. So you have a Gaussian, so this is not an orthogonal basis, but that is very handy for electromagnetic forces because you can actually set up a recursion formula to calculate these integrals on the fly when you need them. And that's very efficient because sometimes you can have a monster basis and then you would have terabytes of matrix elements to store, and then it becomes inefficient. So tomorrow we are going to start and pick up from here. That would be the final thing. And then we will start with second quantization.